Qualitative variables are essential for capturing the richness of economic reality, gender, war, seasonality, and policy shifts within a mathematical framework. Economic data comes in two main flavors, quantitative and qualitative. Quantitative variables, like GDP or inflation, are naturally numeric and can be used directly in regression analysis. Qualitative variables, such as gender, season, or location, represent categories or attributes. They are text labels, not numbers, and regression models, being mathematical equations like y equals beta x plus u, cannot process them directly. The solution is the dummy variable. It acts as a translator, converting these non-numeric categories into a binary format of zeros and ones that statistical software can understand and analyze. For instance, we can't regress wages on the word female, but we can create a dummy variable. Let's call it d_female, which equals 1 if the person is female and 0 otherwise. Now, the model can calculate the effect of being female on wages. This decision map guides us in selecting the right method for creating dummy variables based on the nature of our non-numeric data. First, consider if your data represents categorical attributes like gender or region, or if it's related to time, such as specific dates or crises. If it's categorical attributes, the next step is to determine the number of categories. For two categories, a simple binary dummy variable, typically 0 or 1, is sufficient. If you have many categories, such as different states or industries, you'll need polycotomous dummies, which means creating multiple dummy variables, often efficiently done via the @expand function. Now, if your non-numeric data is time-based, consider its frequency. For recurring patterns, like quarterly sales spikes or monthly effects, you'd use seasonal dummies, often generated with the @cease function. However, if it's a one-time significant event, like a policy change or a financial crisis, this indicates a structural break, requiring a pulse or step dummy. Remember the strategic question: are you modeling a shift in the starting point, intercept, or a change in behavior, slope? This helps in deciding if you need a simple dummy or an interaction term for slope changes. As a key concept, structural breaks often require modeling both an intercept shift and a slope change to fully capture their impact. For full control and complex conditions, you can create dummies manually using logic generators. For instance, you could create a dummy for a period of war combined with high inflation. A more efficient method for binary splits is the @recode function. You provide a condition, and it assigns a 1 if true and a 0 if false. It's clean and simple. The most powerful tool, especially for panel data with many categories, is the @expand command. It automatically creates a separate dummy variable for every unique value in a series, saving you from manually creating dozens or even hundreds of variables. For example, if you have a dataset with a state name column for all 50 US states, instead of writing 49 series commands, you can simply type @expand state name to generate all the necessary dummy variables in one go. EViews offers flexibility ranging from manual control to automated handling of complex categories, and all these methods ultimately produce numeric series containing only zeros and ones. This slide delves into the fundamental mathematics behind using binary variables in a regression model. The core equation presented is yi equals alpha plus beta1 di plus beta2 xi plus ui. Here, di is our dummy variable, taking a value of 1 for the treated or active category and 0 for the base or reference category. For instance, if di equals 1 for females and di equals 0 for males, then males are the base category. When di equals 0, the intercept for the base category is simply alpha. However, when di equals 1, the intercept shifts to alpha plus beta 1. This means the coefficient beta 1 is not an absolute intercept, it's a differential intercept. It precisely measures the shift or difference in the intercept for the treated group relative to the base group, not the absolute value of the intercept itself. A crucial takeaway here is to always clearly identify your base category first, as all interpretations of the dummy variable coefficient will be relative to this base. This model is based on Gujarati 2020, equation 9.2.1. The dummy variable trap is a scenario of perfect multicollinearity. It occurs when you include a dummy variable for every category of a qualitative variable, in addition to an intercept term in the model. For example, if you have a dummy for male and a dummy for female, the sum of these two dummies for any observation will always be 1. The intercept term in a regression is also effectively a variable that is always 1. This perfect correlation makes it impossible for the software to estimate the coefficients. The solution is the M-1 rule. If your qualitative variable has m categories, you must include only m-1 dummy variables in the model when an intercept is present. The category you leave out becomes the base or reference category. Alternatively, you can include dummies for all m categories, but then you must drop the intercept term from the regression. The first approach is far more common. A simple dummy variable, as we've seen, causes an intercept shift. This represents a change in the starting level of the dependent variable between groups, assuming the relationship's rate of change is the same for both. The two regression lines are parallel, as shown in the graph for d equals 0 and d equals 1, with the shift, beta 1, representing the difference in intercepts. In contrast, a slope shift represents a change in behavior or the rate of response. It means the effect of the independent variable x on y is different for the two groups. The regression lines will have different angles. To model a slope change, we use an interaction term. This is created by multiplying the dummy variable d by a continuous variable x. The full model becomes y equals alpha plus beta 1d plus beta 2x plus beta 3 times d times x. The coefficient on the interaction term, beta 3, measures the difference in the slopes between the two groups. If beta 3 is statistically significant, it implies a fundamental difference in the behavioral relationship or rate of change between groups. This is a powerful way to test for structural differences. EViews provides multiple ways to create variables. The most straightforward for beginners is the menu-driven approach. You can navigate through Quick, Generate Series to open the dialog box. In the Enter Equation field, you'll type your logical condition. For example, to create a dummy for a crisis period, you might type crisis equals at year greater than or equal to 2008. For those who prefer speed and efficiency, EViews has a powerful command window. Simply typing gen followed by your equation, like gen crisis equals at year greater than or equal to 2008, achieves the same result without any clicks. EViews has built-in functions that make creating time-based dummies very easy. The @year function extracts the year from a date. Similarly, the @month function extracts the month as a number from 1 to 12. This is perfect for creating dummies for specific months, like a January effect in stock returns. For a specific date, the @dateVal function converts a text string into an EViews readable date format. This allows you to create dummies for periods before or after a precise historical event. The underlying mechanism is Boolean logic. Any logical statement in EViews, such as @year greater than or equal to 2008, is automatically evaluated. It returns a 1 if the statement is true for that observation and a 0 if it is false, creating the dummy variable instantly. These date-based dummies are perfect for modeling policy eras, such as pre-COVID versus post-COVID. The recode function is a versatile tool for creating binary dummies based on a condition. Its syntax is recode, condition, value if true, value if false. It's very explicit and clear for simple binary splits, as shown with the example creating a male dummy. The expand function is the powerhouse for handling variables with many categories. It automatically generates a set of dummy variables for every unique value it finds in the specified series. This offers great efficiency, as it's the fastest way to handle large categorical sets, such as 50 states or 20 industries. Crucially, Expand has options to help you automatically avoid the dummy variable trap. Using drop first or drop last within the command tells EViews to create dummies for all categories except the first or last one, which then serves as the reference category. This built-in safety measure ensures your regression matrix doesn't crash due to singularity, saving you from common multicollinearity errors. Our first case study aims to estimate the effect of gender on wages using CPS, Current Population Survey, data. Our dependent variable is the natural log of hourly wage, ln wage. The independent variables are EDUC, representing years of education, and FE, a categorical variable for gender. Before running any regression, it's a critical pre-flight check to examine the frequency distribution of your categorical variable. You need to ensure you have a sufficient number of observations in each category to get reliable estimates. In EViews, you can easily do this by going to View, Descriptive Statistics, Stats by Classification. As we can see here, we have 180 observations for males and 150 for females, which is a healthy sample for both groups. To estimate our model in EViews, we open the Equation Estimation dialog. The command ls stands for least squares. The full command is ls ln wage c educate at expand fe at drop first. Let's break this down. We are regressing ln wage on an intercept c, educate, and the expanded dummies for our gender variable fe. The key part is at expand fe at drop first. This tells EViews to create dummy variables for the FE series, but to drop the first category to serve as the reference group, thus avoiding the dummy variable trap. The output table shows the estimated coefficients for our variables. Notice that because we didn't use @dropFirst in this specific screenshot, EViews has estimated coefficients for both FE equals male and FE equals female, which would cause an error if an intercept C was also included. The note clarifies that with @dropFirst, one would be missing. If the FE variable was coded with female as the first category and male as the second, @expandFE, @dropFirst, would result in EViews only including a dummy for male in the regression. The coefficient on this male dummy would then represent the difference in log wages for males compared to females. Running the regression is just the first step. The real skill lies in correctly interpreting the output. Let's analyze these results. Looking at the output, the coefficient on FE equals male is 0.779. This coefficient measures the difference in the average log wage between the male group and the base group, holding education constant. The p-value, listed under prob, is 0.0000. Since this is much less than the standard significance level of 0.05, we conclude that the coefficient is statistically significant. There is a meaningful wage difference. Because our dependent variable is in log form, we can't interpret the coefficient directly. We use the Halvorsen-Palmquist formula to find the percentage change, which is approximately e to the beta minus 1 times 100. Plugging in our coefficient, we get e to the 0.779 minus 1 times 100. This calculation will give us the percentage difference in wages for males compared to the reference group, after controlling for the effect of education. This isolates the gender effect after controlling for education. Time series data, especially at quarterly or monthly frequencies, often exhibits strong seasonal patterns. For example, retail sales consistently spike in the fourth quarter, Q4, due to holidays. This seasonal noise can obscure the underlying trend. EViews provides the convenient @sees function to handle this. @seesX creates a dummy variable that equals 1 for quarter X and 0 otherwise. The function automatically detects if your data is quarterly or monthly. To deseasonalize the data, we include seasonal dummies in the regression. The command ls_sales c trend @sees1, @sees2, @sees3 regresses sales on a constant, a time trend, and dummies for the first 3 quarters. Notice we only include 3 dummies for 4 quarters. This is the M-1 rule in action. Q4 is the omitted base category. It's crucial not to include @sees1 through @sees4 and the intercept, as this causes the dummy variable trap. The blue line on the graph shows the seasonally adjusted trend, which reveals the true growth path once the seasonal spikes are accounted for by the dummies. This slide presents case study C, focusing on structural breaks using interaction terms. We're investigating if the 2008 financial crisis altered the market risk, or beta, of a particular asset. This analysis is conceptually similar to a Chow test. To conduct this, we first create a dummy variable, D, which takes a value of 1 for years 2008 and later, using the command gener_d equals @year greater than equal to 2008. Next, we generate an interaction term by multiplying this dummy with market return, using gener_interaction equals d times market return. Finally, we estimate the regression model, LS stock ret C market ret D interaction. The key finding is in the coefficient of the interaction term, dummy times market x. In our results, its coefficient is minus 0.434852 with a p-value of 0.2680. Since this p-value is greater than 0.05, we conclude that the interaction coefficient is not statistically significant. This means we do not have sufficient evidence to say that the structural relationship, specifically the slope or beta, of the asset significantly changed after the 2008 financial crisis. If this interaction had been significant and negative, it would imply the asset became less sensitive to the market after the break. The most common error you'll encounter is the near singular metrics error. This is almost always caused by falling into the dummy variable trap. The fix is simple: remove one of the dummy variables or remove the intercept term. Another common issue, especially in cross-sectional data, is heteroscedasticity. This means the variance of the error term is not constant across observations. For example, the variance of wages might be much larger for high-income earners than for low-income earners. If heteroscedasticity is present, your standard errors will be incorrect, leading to unreliable hypothesis tests. The fix in EViews is to use White's heteroscedasticity consistent standard errors, which can be easily done by adding the option cov equals White in your estimation. After running a regression, you notice the standard errors on your dummy variable seem unusually large. As a best practice, you should check the correlation matrix of your independent variables. If you see correlations of 1 or -1, you've likely fallen into the dummy variable trap. Here is a quick reference for the EView syntax we've discussed. For creation, series x equals condition uses Boolean logic to create a 0-1 dummy. The @recode function gives you more explicit control, while @seasX is your go-to for seasonal dummies. For regression, the basic syntax is LSYC, where LS is least squares and C is the intercept. To include dummies while avoiding the trap, use @expand x @dropFirst. Finally, to create an interaction term, you simply use the multiplication operator, d times x. Don't forget EViews is not case-sensitive, so @year equals @year. This cheat sheet is a quick reference for your research projects. Thank you for joining this presentation.